Good morning, everybody. Well, today we're going to do an exercise or two on measurable functions, and then we're going to go straight into the Lebesgue integral, which is exciting. But I did want to let you know that we have some guests today in the class, and so here they are. Fred. Okay. Then we have Slopey. And we have Hermione. And I know what you're thinking, but her mother really liked polar bears, even though Hermione's Patronus is an otter. But anyway, let's get going with questions about measurable functions and the Lebesgue. You're really excited. All right, so here we are. Here's the exercise. Give an example or show none exists. All right, so number one is a non-measurable function g and a measurable function h such that h composed g is measurable. So number two, I'll go through all of them, then we'll vote and figure out. All right. So number two is a continuous function that is not measurable. Three is a measurable function f capital F, and an open set U in R such that capital F inverse of U is not measurable. Okay. And then number four is a continuous function capital G such that and a measurable set. All of our measurable functions are going to be on R or Rn, something simple, okay? And a measurable set S such that G inverse of S is not measurable. So the inverse image of the set and thing. All right. So let's do some voting. All right. All right, so the first one, I guess true will be that yes, an example exists. False would be no, an example doesn't exist. All right, so let's go. All right, so let's see, Slopey, Hermione, and Fred, are you guys ready? All right, close your eyes. All right, so number one, non-measurable function g and a measurable function h such that h composed g is measurable. True or false? Okay, true. Okay. False. Okay, wait a minute, guys. Yeah, these numbers should add up to 3. So something must be wrong. You have to pick one, true or false. Yeah, Fred, I know you like things that are both true and false, but Okay, let's try that again. Okay, here we go. All right, just pick one. Okay, true. False. Okay, that was much better. They added up 3. Very good. All right, let's do the next one. Continuous function that is not measurable. How many people for true? False. Okay. How about for number 3? A measurable function f and an open set u such that f inverse of u is not measurable. True. False. Okay. And then finally, a continuous function g in a measurable set s such that g inverse of s is not measurable. True. False. Okay. Well, it looks like you're pretty consistent. And yeah, Slopey, I see that you really like 2s and 1s in that order. Okay, very good. All right, so let's actually maybe actually figure out using logic whether these things are true or false. All right, so let's think about this. A non-measurable function g and a measurable function h such that h composed g is measurable. All right. Well, first of all, how do you even make a non-measurable function? Hermione? Oh, very good, Hermione. You are a smart one. Anyway, it's that's right. It's because if you want to make one, you could just have constant values on non-measurable sets, which we already know they exist because, for example, we had that example of 0, 1, and we divided it up into a bunch of non-measurable sets. All right, so yeah, so that would be a way to construct it. So we could have, like one of those non-measurable sets in 0, 1 where it's 1, and then everywhere else it's 0 or something like that. Okay. Now, how could we make something that's, or, we could pick other numbers, 10, 75, whatever. But just if its values are on a non-measurable set, then if you did the thing where the inverse image of an interval, you would get something that was that non-measurable set. So it can't be a measurable function. Yeah. So how can we do this then? Slopey? Oh, man, that was a slick way to do it. Good job. So the answer is true. So take E, a non-measurable subset of 0, 1. Define, okay, this is how we're going to define our non-measurable function. Define g from 0, 1 to r by g of x equals 1 if x is in E, and then negative 1 if x is not in E. And then let h of x, can somebody else guess? Yep. Equal absolute value of x, which is measurable. And this is not measurable. Then look at what is h composed g going from 0, 1 to 0, 1. Is the constant function 1. Which is measurable. Very good. Yeah. Okay. Cool. So, you guys are good at that. All right. Second, oh, and by the way, if you wanted it to go from all of r to r, you could just have both functions be 0. out of, or leave h of x as that, and then just have g be 0 outside of the interval 0 and 1. Okay, great. So a continuous function that is not measurable. Fred, I bet you know the answer to this. Uh-huh. Yes. Good job. Yeah, so, right, that's actually impossible. Okay, so let's see. What did we get so far? We got that one, and then we got that one. Oh, the voting method didn't work on that one. But artistically it worked, because 2, 1, 2, 1. Yeah, right. All right, but anyway. So why is that true? Well, you need to show that if f is continuous, and I think this is a homework problem, so I'm not going to completely give it away, but it has to do with, to check if something's measurable, we need to consider f inverse of the interval from alpha infinity for all alpha in R, right? And guess what? That's an open set. And what do you know about continuous functions? Okay, I think you got it. And so the result, this whole thing will be measurable. Okay, right? So that means it's impossible to have something not measurable. Okay, good. All right, so now we're getting to the harder stuff. So we want a measurable function f in an open set U in R such that the inverse image of U is not measurable. This is a much harder one. What are Slopey and Hermione, what are you guys talking about? Yes, yeah, that is tricky. So it's good to kind of think of it one step at a time. Well, note, if U is an interval, open interval, AB, which is, let's see, how can we write this? A infinity intersect B infinity, then capital F inverse of AB has to equal capital F inverse of A infinity intersect B infinity, which means it's, and this is a set theory fact. Yeah, the inverse image is very interesting with respect to intersections and unions. It's exactly what you think it would be. You can separate it out, but that doesn't work with just the function, only the inverse image. It's really interesting. Okay, but right, because if something lands here, it has to land here, so it's in this, and it has to land in the other one. And then it's exactly the things that land, and then both of these are measurable. And so the result is something that's, it's measurable. But then you can use the fact that every open interval in R is a countable union of disjoint open intervals. Then use countable additivity and you get that f inverse of any open. Oh, whoops! I meant to say set here. And any open set in R is a countable union of disjoint open units. So in other words, it will be a countable when you take the inverse image of any open set. It will be a countable union of stuff like that. It's got to be measurable. So that tells us that 3 must be false. Great. Okay. Good stuff. All right. Now let's do the last one, which is, okay, let me remind you, I'll stick it over here. Okay. Here we go. Yeah. So a continuous function g and a measurable set S such that g inverse of S is not measurable. I'm just going to give you the answer for that. It is possible, but it's a complicated example. What it is you use the Cantor-Lebesgue function and add something to it, so like x, and then you can get an invertible continuous function whose inverse is continuous. But then if you work it out, you can find an actual non-measurable set whose inverse image is not is not measurable. You have to go the other way. But anyway, it's a complicated example, so it is true. So yeah, that's the weird thing about composition. You can take and even a continuous function, and so continuous and measurable functions do not preserve measurability of sets or the inverse images. They don't work either way. So anyway, so let's see. Let's go back to our tabulation here. Let's see. So 3 was false, and 4 was true. Okay, not bad. Good job. All right. So next, we're ready to start with the Lebesgue integral. I bet you're excited.